Hey everyone, welcome back and let's write some more neat code today. So today let's solve the problem, build a matrix with conditions. Okay, so since we all got things to do and places to be, I'm gonna try to make this quick. Don't hold me to that though. So the first thing I'm gonna do is just go through the problem description because to be honest, it's kind of long and pretty complicated. Second, I'm gonna show you that the intuition to solve this problem is actually very similar to yesterday's problem, well at least trying to figure out the general idea. Third, I'm gonna explain the core algorithms you're gonna need because even if you're a genius and you kind of know how to solve the problem, the algorithms themselves are actually kind of complicated. That's why I always say that you should know algorithms like DFS very, very well, because when you get to a problem like this, DFS is only a small part of this problem. Finally, we're going to code it up in Python. Lastly, when I'm done with that, I'm probably going to take a break because to be honest, it's been a long week and I'm sure you might feel the same. So let's get into it. The idea is, let's focus on the example. We're given K. So that tells us the dimensions of the output matrix that we want. So it's going to be K by K. It's going to be a square matrix. Next, we're given these two input arrays. This is kind of the complexity of the problem. What the first array is saying is that these two numbers are going to, well, first of all, let me just say that the only values in this are going to be the numbers 1 through K. The only values in column conditions are going to be the numbers 1 through K. And we want to take the numbers 1 through K and put them in this square matrix. Now, that might sound confusing because if we have a K by K matrix, how can we fill it with just K elements? Well, the remaining elements are going to be 0. So only K elements are going to be populated 1 through K. Obviously, in this example, K is 3. So what the first array row conditions tells us is that 1 will be in a row above the value 2. So theoretically, we could have had 1 over here and 2 over here, or we could have had 1 over here and 2 over here, or we could have had 1 over here and 2 over here, and that's what we ended up with. Now there's a second condition, 3, 2. So 3 has to be above 2. 2 could have been here, or it could have been here, or maybe 3 could have been here, and then 2 could have been down there. So it's a little bit ambiguous, isn't it? Right now the ordering is 3, 1, 2 for the rows. We could have, I think, had 1, 3, 2, because all we need is 1 to be above 2 and 3 to be above 2, and I think both of these satisfy that condition. When they say above, it needs to be strictly above so they can never share the same row. The second array, column conditions, is pretty much the exact same thing except for column. So if we have 2, 1, we say 2 has to be to the left of 1. It could have been like this, or it could have been, like this, or it could have been like this. Now, once you realize that, these are saying it needs to be strictly different, like it needs to be above, or with the columns, it needs to be to the left. You kind of realize that every single element in the matrix is going to have its own row and its own column. That's kind of an important observation to make, right? Like here you can see everything has its own row and own column. So this kind of makes the problem seem like it's not the end of the world. Doesn't mean it's easy, but I'm about to show you how you can actually make it easy for yourself. Look, I'm not going to lie to you. I still don't know how to solve this problem. So what can we do? Let's just try to simplify it for a second. Forget about the columns. Let's take this two-dimensional problem and turn it into a one-dimensional problem. If we only had to deal with rows, how would you solve the problem? Well, I don't know about you, but this is kind of giving me vibes from the problem course schedule. If that's not enough, maybe you've solved that crazy hard problem, Alien Dictionary. Is it giving you similar vibes? Because it is for me. If we only have one array, it's basically saying that 1 is a prerequisite of 2. Like 1 is like a directed edge kind of, right? Like 1 is going to be above 2. And we're also saying 3 is going to be above 2 as well. So if we were actually to draw it as an entire graph, we'd have a graph that looks like this. And this is only for the rows, by the way. So now it kind of becomes clear. Well, it becomes clear if you've heard of the algorithm topological, I don't know how to spell today, I'm really sorry, topological sort. If you don't know what this algorithm is, I'll try to teach it to you because it's not super bad, but at the very least, I hope you do have a decent understanding of DFS. If not, I have plenty of other videos. You can check out leetcode.io, but definitely get a good understanding of DFS before attempting this. Because what topological sort says is, what is a valid way that we could order the values in this graph so that they're actually visited in the order that the edges are represented, such that basically for us to visit 2, we visit all of its prerequisites first. So basically, one valid ordering would be 1, 3, and then 2, or 3, 1, and then 2. So like those 2 orderings I said would work. Now we've kind of solved the problem in 1 dimensions. If we didn't have to worry about a matrix, if we were just ordering the values on which like row each element is going to go in, we've pretty much solved the problem, haven't we? Okay, but that's not enough. Because if we say, okay, we have 3, 1, 2, well, we got to put these in different columns. Well, can we just take the exact same technique and apply it to the columns? Why not? I'm going to do exactly that, and let's just try it and see what happens. So down here, I'm going to have the columns graph. I'm going to take these edges, build a graph. In terms of code, we generally use something called an adjacency list. So that's what I would do, but visually, it's going to be looking something like this. So 2 goes into 1, and 3 goes into 2. Okay, so this time it's actually very straightforward. There is not a choice here. It has to be in this order, meaning the columns, the first column has to be 3, the second column has to be 2, and the first column has to be 1. Okay, so that makes sense so far, and we've pretty much solved the problem. If you don't understand it, let me kind of draw it out for you. Suppose I took one of those valid orderings from the row. Let's just represent it in terms of a list, and I'll kind of do it consistent with this example. So let's say we did 3 first, and then 1, and then 2. These are the orderings of the rows. And then same thing for this. We got 3, 2, 1. This is the ordering of the columns. Now, what does this tell us? It might not seem obvious, but if 3 is in the first position, it's going to go in the first row, meaning it's going to go in row 0. 1 is in the second, it's going to go in row 1. 2 is in the last position, it's going to go in row 2. 3 is going to go in column 0. This is going to go in column 1. This is going to go in column 2. So basically, the index that each element shows up in is going to be the coordinate it's going to be assigned. So 3, you can see 3 is at row 0 and column 0, so it's going to go obviously at 0, 0. 1 is at row 1 and column 2, so it's going to go at row 1 and column index 2, so right over there. Lastly, 2 is at row 2, column 1, so it's going to go at row 2, column 1, and that's exactly it. Look, we just did it. Conceptually, it's not super crazy. Even this, by the way, like I drew this out like it's so simple, but even this, in terms of code, how do you think you'd code this up? Because the way I filled this in was number by number. So the way we're going to code this up is actually by converting this into a hash map, but that's a minor detail I think can be explained more easily in the code explanation. We're actually not quite done with the drawing explanation yet. There's a couple other things we have to cover. One is going to be, how does topological sort work? How am I going to implement it? It's very similar to DFS with a couple differences. Second, there is an edge case that we do have to consider because it's possible that the matrix is not valid. Let me actually start with that. Can you think of what would have to happen for the matrix to not be valid? Well, we need a contradiction, right? So what if I said, okay, row 1 is above row 2. This is a 1 edge. Row 2 is above row 3. And then I tell you, well, row 3 is above row 1. Do you see the contradiction? Like if I put 1 here and then I put 2 down here and then 2 is above 3, how can 3 be above 1? It's a contradiction. So how would the graph for this look like? Let's say something like this, 1 to 2, 2 to 3, and then 3 to 1. Now you might see, we know it's invalid if either of the graphs, either the row graph or the column graph, has a cycle. Then it's invalid. We'll get stuck in like an infinite loop. Now, how would you detect that there is a cycle? Because consider this for a second. Just consider like a random looking graph that looks something like this. 1 maybe goes into 2 and 3, and then both of these go into something called 4. Like imagine we have a graph that looks something like this. This does not count as a cycle. It doesn't count as a cycle because from 1 we can go to 3 and then we go to 4. That's it. Then we go back to 3, we go back to 1, and then from there we go to 2 and we get back to 4. Yes, we visited the same one twice, but that doesn't mean there's a cycle. A cycle would mean that along the same path, we keep going and then we get back to a previously visited node. This is not a cycle because we go here and then that's the dead end. Then we go all the way back and then we go down here and then we go all the way back. I don't see the cycle here because there isn't a cycle in this graph. So the way I'm going to detect cycles is by having one hash set for visited, because we don't want to have repeated work. We don't want to end up visiting the same node twice. Consider if this one had some descendants and we wouldn't want to have to traverse them multiple times. So that's going to be one hash set, but the hash set that's going to detect cycles, I'm going to call it the path hash set, and I'm always going to add every node that's along the current path in that hash set. If we pop back, I'm going to remove that node from the hash set, but nothing is ever going to be removed from the visit hash set. So that's the small distinction. And that's pretty much the main distinction. The only other point that you need to know in terms of like how I'm going to implement topological sort, there are a couple ways to do it, but I'll show you why I prefer doing it the way I'm going to show you. Consider pretty much the same graph actually, and then maybe like we have some choices here. Like we have a 5 here, and believe it or not, topological sort works on a disjointed graph. So you can see these are all connected, but imagine I had 6 and it connects to 7, and imagine I had like 8 to 9. So imagine a graph like this. How is topological sort going to work? Well, basically, these ones are pretty straightforward. The topological sort of this would just be 8, 9. The topological sort of this would just be 6, 7. The topological sort of this would be more interesting. There'd be more choices here. So we definitely have to start with 1, and then we have a choice of either 3 or 2. Let's pick 3. We can't go to 4 yet because we haven't met the prerequisite. So we have to also have 2 here. Now that we have 1, we have 3, 2. We can either pick 4 or 5. The order of these doesn't really matter. We could have it either way. I'll just write it like this. With topological sort, it's non-deterministic. There could be multiple correct solutions. Well, I don't know if non-deterministic is the best word to describe it, but it could have multiple orderings. So how would we actually arrive at this in terms of code? Well, the way I prefer to do it, and you might have a different opinion, I run a depth-first search. I run the depth-first search until we get to the base case. So this is what I would do. I would have my output array, which is going to be the topological sort ordering. I'm going to get to 1. I'm not going to add it yet. I might add this to the visit hash set, but I'm not going to add it to the output yet. I'm going to do it in reverse order. I'm going to get to 1. I'm going to get to 2. Then I'm going to get to 5. Okay, 5 is the one that doesn't have any more descendants. It's kind of the base case. So I'm going to add it at the beginning. I'm going to go back up to 2. I can't add 2 yet. I'm not going to add 2 to the output yet. I'm going to wait until I do all of its descendants. So 4 is one of the descendants. Now I'm going to add 4 to it. And now that I've done both of its descendants, now I'm going to add 2 to the topological sort output. And then I'm going to pop back up to 1. And I haven't done all of 1's descendants yet, so now I'm going to go to 3, and then I'm going to do all of its descendants. Its descendants have already been visited, so I'm going to go back. Now 3, all of its neighbors have been finished, so I'm going to add 3 to the output ordering, and then I'm going to pop back up to 1. Everything's been finished, so we can go ahead and add 1 to the output. The only thing about this is it's not what we want, but it's an easy thing for us to fix. Just take this and reverse it. That's it. Because with topological sort, what we're trying to do is visit each node before we do all of its descendants. It seems like it might be easy to do, but this example will show you it's not. If I tried to do, okay, add 1, then add 2, then add 5, okay, it seems like it's working so far, then add 4, and then we go back up to 1, and then we add 3. Well, do you see the contradiction? How did we have 4 before we added the 3? That's why it's easier to code up if you do it in reverse order. You add these, the nodes that don't have any more descendants, you add them first, and then you can just reverse the output. So that's pretty much everything you need to know to solve this problem. And in terms of a time complexity, I assume that there's not going to be any duplicates in here. So it's basically going to be bottlenecked based on the traversal, which we're going to run 2 times, but that's a constant, so it doesn't matter. So how big could one of these graphs possibly be? I guess in the worst case, each value could be connected to every other value. So I think in the worst case, that's k squared. So this is like the literal worst case. I don't think it'll actually be that much. So I guess it's either k squared or the maximum of either of these two. It's going to be the minimum of those. So I guess, just take the length of either of these. Actually, now that I think if we're going to be creating a matrix like this, I think k squared is probably the most appropriate way to put it. So I'll be leaving it at that. So now let's code it up. I don't know how helpful this is, but this is the train of thought that I had. You can see it's going to be kind of a lot of code, so I'll try to keep it relatively organized. So the way this is going to work is we're going to run topological sort, but remember the example I showed you where we had a disjointed graph, where the graph isn't connected? We can't just pick one random node in the graph and then run topological sort on it. We might have to run topological sort from literally every node in the graph, and we can mark them visited as we go. So that's why we're actually going to split this up into 2 different helper functions. I'm going to have one helper function for topological sort. It's just going to take in the list of edges, either this or this. And we're also going to have a function for depth first search. That's the one where kind of the bulk of the work is going to be done. So let's just think about it abstracted for a second. Let's think about it from a high level. The way I'm going to be calling topological sort is like this. I'm going to call it twice, passing in row conditions the first time, and I'm going to be passing in column conditions the second time. And what we expect this to return is pretty much what I had in the drawing. This is going to return the row order of the numbers, the order that the numbers should appear in terms of the row. The other one is, of course, going to do the column order. So these are going to be arrays. These are going to be lists. The way I'm going to code up the topological sort is if there's a cycle, I'm going to detect that by returning an empty array. So if either of these is an empty array, if not row order or not column order, then we're going to return an empty array because that's what they pretty much told us to do in the problem description. If that's not the case, assume that you already have these two. Maybe in your real interview, you don't know the implementation details of either DFS or topological sort, but you know that those are required to solve the problem. I think it's better to actually start with this part of the code because then at least you know where you're going. If you can implement these, you can solve the problem. So here, what I'm going to say is we have these, but what we're trying to do is populate the result matrix. So I'm actually going to initialize that down here in Python. It's pretty straightforward to do. It's going to be k by k, so something like this. And now I want to go through every number from 1 to k, num in range 1 through k, and I want to say that at some row column position, I want to assign this num, but we don't know which row that this number belongs to or which column it belongs to. But the fact that we have the column and row ordering, we can get that. With these data structures, we wouldn't be able to get it in constant time. So I'm going to convert these two lists into hash maps or dictionaries in Python. So I'm going to say before this over here, I'm going to say value to row hash map. And you could probably code this part up like in your language of choice. In Python, I'm going to try to keep it concise because this is going to be a long enough solution as it is. So I'm going to use something called dictionary comprehension. Right now, I'm also going to enumerate. I'm going to say for in enumerate row order. So this will give us the index and the number in that array. Of course, we want the number to be mapped to the index, which tells us the row. So I'm going to say n maps to I. I'm going to copy this and just update it slightly by renaming this to value to column and renaming this column order. So it's going to do the exact same thing for column order. So then down here, I'm going to look up the row and column with these two data structures, just like that. And assuming we do that, we should have the result. And we can guarantee that row order and column order, if they're non-empty, are going to include every number from 1 through k. Because even if the graph is not connected, even if it's a disjointed graph, we're going to visit every edge. And I'm going to show you that part right now. I just happen to know it off the top of my head because I know how topological sort works at a pretty decent level. This is like an advanced algorithm, which is why I cover it in my advanced algorithms course. I don't expect you to be an expert on this. So if we're passing in the list of lists, generally that's not how we want to run a DFS. So the first thing we're actually going to do in here is convert it into an adjacency list. So I'm going to call it adjacent default dict, and I'm going to pass in list. And so that will make it easy for us to do this for source destination in edges, because we know we're dealing with directed edges here. So I'm going to say that for this source node, I'm going to append to its neighbors this destination node. So that's just initializing the adjacency list. The next thing we would want to do over here is go through every source from 1 through k. So I'm going to say 1 through k plus 1. And then run a DFS on it. Now, of course, we're going to have to pass in the source node to run the DFS, but there's a few other things we're going to have to pass in as well. Another thing will be the adjacency list, obviously. Another thing is going to be the 2 hash sets that I talked about. We want to mark positions visited. We don't want to get stuck in an infinite loop. And we also want to be able to detect a cycle. So we're going to create 2 hash sets for those. I'm going to just copy that right there. There is one last parameter we're going to pass in. It's going to actually be an array. I'm going to call it order, because remember, ultimately what we're trying to do is collect the order. So that's kind of what I showed in the drawing explanation. When we reach the base case in DFS, that's when we will append a node. Or not even a base case, but once we've visited all the neighbors of a given node. So here I will create an array for the order. And then remember, before you return the order, you definitely want to make sure to reverse it. In Python, you can do that pretty easily like this. And here I'm just going to make a comment that that's reversing it. Now, what about cycle detection? The way I'm going to detect a cycle is like this. That's actually the first thing I'm going to do in the DFS, other than, I guess, assign what parameters we're going to have for it. So all these parameters. So if source is in path, and the other one is if source is in a visit. I very specifically put this one first, because if a source node is along the path that we're already on, then we detected a cycle. If that's true, though, this is also going to be true. We want to know if this one is true more, because this is the case where we've detected a cycle, and that's when we're going to return false. In the other case down here, I'm going to return true. This might make more sense when I finish the rest of the function, because as you'll see, when we get to a node, we're going to mark it as visited immediately. Add this to visit, so source. Also, I'm going to say add it to the path, just like that. And then I'm going to run my DFS somewhere over here. And then when I'm done with that, I'm going to say, okay, now path.remove this node. But we're never going to remove a node from visit. Once a node is visited, it should never be visited multiple times. Okay, so now the actual DFS part, it's not super crazy. Let's go through every neighbor of the current node. That's exactly why we have the adjacency list. So source. Now we run DFS on the neighbors, so passing in the same adjacency list, same visit hash set, same path hash set, and same order array. Now, what if we returned false from one of the base cases? Like, what if we return false from here? What should we do in this case? Well, probably return false immediately, because once you detect a cycle, there's no point in continuing. So as soon as we see it, if not this, then just return false. No need to visit the remaining neighbors. If we never detect a cycle, though, down here, let's just go ahead and return true. There's only a couple things left. First of all, the order variable, we haven't really used it anywhere, and that's because we're saving it. Once we go through all the neighbors of a given node, at the end, after all that is when we append the current node. So that's just the DFS portion. Okay, I actually did have a typo, so this is going to be source, sorry. And I think we're actually nearly done. I'm just going to quickly read through the rest of the code. So I think the DFS looks good. It's very easy to make a bug in a solution like this where there's so much code. So that's another challenging part about this. Here, if the DFS returns false, so if not DFS here, then we should return an empty array. There's no need to continue running DFS, and we definitely don't want to return the values that have already been added here. At this point, we return an empty array so that here we can detect that and then return an empty array. Now, before you call DFS, you could check if source has already been visited, but that's literally a base case in the DFS, so it'll execute immediately anyway, so I don't think it's necessary to have that line here. But here we're calling topological sort, getting the output orderings. This is the case where we detected the cycle. Then otherwise we convert it into the hash set. Down here, we initialize the matrix. We get the row and column. Here, actually, I think I messed this up. These are hash maps. We want to look up this number. We want to map it to its row. So I'm going to fix that. And here, we want to map that to its column. So I'm going to do that as well. Now I think this is pretty much correct, but it's hard to fit it all on one screen. Yeah, I don't think it's possible to fit it all on one screen. I'm really sorry. I'm trying my best. It's just really, it's 40 lines of code. We should be able to get it. So that's the best I can do. You might have to zoom in, but I'm going to run it and it does look like it works and it's pretty efficient. If you made it this far, good job. Give yourself a pat on the back. I'm going to go take a break. Thanks for watching and I'll see you soon.